It also means that like you should understand how ions change, right? Ions change because we gain or lose electrons. Isotopes change because we gain or lose neutrons. And if we gain and lose protons, what changes isn't that it becomes an ion and isn't that it becomes an isotope, it becomes a whole new element, right? So protons are how we choose our elements. Everything else will give us ions or isotopes. We should understand how to find the average atomic mass from its different isotopes. We should know where our metals, nonmetals, and metalloids are, and then our group and our periods. Now, for your ACS, ACS does recommend a equation sheet. And if you look at your page from today, it's not linked. I will link that right now. There is a recommended equation sheet that they use. Now, what I would say about their equation sheet is it's very similar to what we already have for our class. Their only difference is some of their numbers have been rounded just a little bit, right? So like the gas constant, instead of 0.08206, it's 0.0821, right? It doesn't really change things all that much. But if you want to get exact numbers with like what they were reporting on their answer key, then you want to use their values, right? So in the same way, their atomic masses are not quite as far out as ours. If you use theirs, then you'll get their numbers right on. And that's the difference between theirs and ours, right? In general, you're supposed to use this one. It also lines up all of their symbols with their equations that they refer to inside of the problem. And so you just want to make sure that you feel comfortable with this as well. It's definitely something that I would have printed out when I do my exam. And you can kind of see how those kind of connect with what we're doing. And so this is going to be our first one. So what I'm going to do is I'm going to run a poll right now, and we're going to do this for question number 44. So when this poll launches, you can go ahead and move it to the side, and then we're going to use this to have our 90 seconds to answer question number 4. So go through and decide which answer should be your question number 4. So right now it's about 45 seconds. It's about half the time. We have about 10 seconds left. All right, and so that's 90 seconds, right? So it goes by pretty quickly. So you want to make sure that you're staying on top of it. Now, when we're going through this, it's asking us, well, we have our 5D orbital. So what elements relate to our D orbital? What do you guys think? What elements relate to our D orbital?
The elements in the middle section. I forgot.
All right, so our transition metals. Very good.
There you go.
And so the ones right in the middle. And so when we're looking for the 5D, the important part to remember is that 5D doesn't happen in the 5th row down. So for those of you that told me that it was silver, silver is 1, 2, 3, 4, 5 down. That's not the 5D though, that is the 4D. When you go into your transition metals, you always have to go up one number. So instead of being silver, we should really be in that row afterwards. So you count down 6 on your periodic table, and you were looking for somewhere in there. So anything from lanthanum to radon all have a 5D electron. And so which iridium is the one that we should be looking for? For our answer. We'll try this again. When the poll pops up, you can always move it to the side if you want to look at the screen for the question, right? And so now we're going to look at number 45. So go ahead and start number 45. So this is about 45 seconds. You have about 15 seconds left. And that would be 90 seconds right there, right? So that think about how the pacing of this. It does go a little bit quickly. Now, when we're looking at this, what does the N correspond to?
The energy level.
The energy level. And what does the L correspond to?
The shape.
The shape. So with our shapes, 0 is going to be an s orbital, 1 is going to be a p orbital. What will 2 be?
D.
D. So we're looking for an electron that's in the 3D. So where's the 3D for our periodic table? What element is in the 3D there?
Titanium.
Titanium, right? So we need to go 4 down, and then we need to be looking in that transition metal grouping. So we really are looking for titanium here because we're looking for that 2. Now the ML tells you the orbitals inside of that D, and the MS tells you the spin of them. But both of those can be any electron inside of that 3D orbital. And that's because they all have the same energy. So we don't know whether ML 0 fills before ML minus 1. And so as long as it's going to be ones that just have those 3D, then we'll be able to identify one of those elements in its ground state. So when in doubt, just start with those first 2 numbers and only go farther than that if you have more than one species that kind of qualifies for it. But in all of the exams I've seen, you pretty much can just get away with only using those first 2 numbers. If they give you the quantum numbers, then you use those first 2, and then you have to look at these other ones to make sure that they make sense. All right, let's try our next one. This is going to be for 46. So you have about 20 seconds left. All right, and that's our 90 seconds. So when we look at this, right, this is asking us about our trends. So beryllium to barium, are they both in the same group or are they both in the same period?
Same group.
Same group, right? So as we go from beryllium to barium, how does our atomic radius trend? It goes up, right? As we go down the groups, so as we add in new energy levels, we should be getting bigger. So we know just from that part that number one has to be one of our options. Now, we should really know our atomic radius trend. That should be the first one that we learn, just because so many of those other things are tied to our atomic radius. How our trend goes for atomic radius, so does a lot of our other trends. From there, we can look at our ionization energy. So is it easier to take an electron away from barium or from beryllium?
Beryllium, right?
So beryllium is a smaller molecule or atom, and it's actually harder for us to remove an electron from beryllium than it is from barium. Barium, because as its size increases, those electrons become farther away from the nucleus, they become a little bit easier for us to take away. So going down the group, our ionization energy gets weaker because it's easier to take away. Going across the period, it gets stronger as the atomic radius gets smaller. So ionization energy goes the opposite direction of our atomic radius. The smaller you are, the higher your ionization energy is. So we know it can't be number two. And then nuclear charge is the tricky one. Nuclear charge, because they're in the same group, you would imagine that they have a similar effective nuclear charge. And the thing to remember is that core electrons don't perfectly shield one proton to one electron. We treat them that way for our approximation, but in reality, they're always going to shield a little bit less. It's kind of like when you sit in the movie theater and there's people sitting in the rows ahead of you. Even if someone's directly in front of you, you still at least see a little bit of the stage around them, right? It doesn't completely block your view. And so that's kind of what's happening with our effective nuclear charge. So even though they have a similar number of valence electrons, barium has a slightly higher nuclear charge because those core electrons don't shield them all completely. That balance in effective nuclear charge is kind of overcome because the size is so much larger, right? And so we ended up with B. Very good. So I'm going to let this next one launch for 47. And then I noticed that there was a question in chat. And so if you want to clarify what you don't get about question 45, then I can answer that for you, Aman. So we're about a minute in. All right, and now our time is up. Now, whenever you see these things with the ions and you're arranging them, right? We've had a couple different questions like this even in our own class, right? So this is an important thing for us to be able to do. What do you guys notice about all of our options that we're presented with here?
They're all ions.
Right? They're all ions. And so we have to take into account what our ions do to their size. So are cations or anions bigger than usual? What do you guys think? Which ones are going to be bigger than usual? Is it going to be a cation where you have lost electrons, or is it going to be an anion where you guys have gained electrons?
Cation.
So when you lose electrons, right, that means that the protons can pull you in closer, right? The size of the atom kind of comes from your electrons having to stay away from each other. So the fewer electrons you have, the closer your atom can be pulled together. The more electrons we put in there, the more that electron repulsion comes up. And so what that kind of means is actually us losing electrons lets us become smaller. When you lose electrons, we get less repulsion. So it's kind of like there's not as many electrons to fight with each other, and so we can pull them in all closer. Now, when we're looking for decreasing size, then that means that our cations, our positive ones, should be towards the right-hand side. So we know that it can't be C. It probably won't be D either, because those are where our cations are kind of bigger than our other ones. Now, the other part is if you look, calcium, potassium, and sulfur, these ions here, what do they share in common?
They all become the argon.
They all have 18 electrons, right? So they all look like argon. And so we can know between those that we should definitely have sulfur as the biggest because it's the one that's an anion. Then we should have potassium because it only has 19 protons. And then we should have calcium with its 2+, because each of those have the same number of electrons. So in a lot of the ways they have the same amount of electron repulsion. The difference is that the number of protons have changed. So the bigger or the more protons you have, the smaller your size should be. The fewer protons you have, the larger your size should be. And so the last one that we need to classify is bromine. And bromine doesn't get the same number of electrons as the other ones, right? Bromine is going to have 36 of them. And so is bromine going to be larger in its size, or is sulfur going to be larger in its size? What do you guys think? If we go to another energy level, are we going to increase in our size or decrease in our size?
Increase.
Increase. So our bromine in its -1 charge, we expect that to be bigger than our sulfur. And so that's how we got B. Right? So when you look at it, when you get these series, especially if they all have the same number of electrons, you want to make sure that you're cation with the highest charge, so your most positive ion, is going to be your smallest one. Your one with the most negative charge is going to be the largest one when they all have the same number of electrons. After that, you have to compare where they started from, right? So that's why we knew bromine was going to be larger than sulfur, even though sulfur has a larger charge. It's because sulfur was a smaller atom to begin with. Now, all of these are kind of related to your periodic table and your trends, right? You do want to make sure that you practice a little bit of your ground states. It seems like our quantum numbers kind of threw some of us off, right? And so when you're looking for your different ones, remember that for an element to have, that every electron has a set of numbers associated with it, right? You get your N, your L, your M sub L, and your M sub S. And so when they talk about different electrons orbitals and where they're located, then we should also have a set of numbers that go with them. So like if we look at 45, what it's asking us is all of this part here is all background information to let you know that it's under standard conditions. It's really just saying which atom could have an electron that's in, and then it's giving us a location, kind of like an address. And so that's what we're looking for those. This feeds over into like our electronic structure a little bit. So this is also talking about like periodic properties for those electronic structures, but this is more about light as well with our quantum numbers and our orbital diagrams as well. So in some ways, this one and the last one has a lot of overlap. It does talk a little bit about magnetism, though I haven't seen that many questions on it. It is something that you do want to know. And remember that paramagnetic means that you have unpaired electrons. Diamagnetic means that all your electrons are paired. Magnetism is a great way for us to make sure that you have the correct orbital diagram. Because if I ask you, because it's hard for me right now online to have you guys draw me pictures with your orbital diagrams, but if I ask you how many paired or unpaired electrons you have, it can make it quite clear whether or not you have the right orbital diagram. So that's kind of the reason why magnetism fits in with that. So let's do some practice one. This is similar to question number 45. And so now we're looking at arsenic, and we would like to figure out how many electrons start with that same set of quantum numbers for those first two. So you want to make sure that you read this question carefully, right? Think about what orbital is related to n equals 3 and L equals 1, right? We should be able to translate that over. Is that the 2s or the 4p or whatever it is, right? We should be able to put that together. We got about 5 seconds left here. So when we're looking for n equals 3 and L equals 1, this means that we should be in energy level 3. And what should the L be? What orbital are we going to be in?
P.
P. So when we look at arsenic, 1, 2, 3, 4, how many electrons does arsenic have in the 3p? We're getting a lot of people saying 3, But when we look at it, the 3p starts with aluminum to argon. Does arsenic only have 3 electrons in that orbital? And that would be no, it actually has that filled. So it doesn't only have 3 electrons there, it really has 6 of them. Oh, I'm not sure why I put 3 there. It should have 6 of them because it's got a full 3p shell. It's the 4, when n equals 4, L equals 1, where we have just 3 electrons. So I made the same mistake that you guys did when I made this answer key. It should be 6 of them in the n equals 3, L equals 1. Okay. Any questions on that part? Then let's try our next one. Now remember what direction your ionization energy should trend for your periodic table, right? It should be the opposite of your size. So as your atomic radius gets smaller, your ionization energy should go up. And so when we look at them, normally for a question like this, I just take my fingers and I put them all on my periodic table, and then I can kind of see where things trend. And so my lowest ionization energy should be my calcium, because it's farthest to the left and farthest to the bottom. Then from there, I know that silicon must be less than phosphorus, and phosphorus must be less than nitrogen. And so we should be looking at question number A. And you guys did well. Looks like everyone's on that part. And so that's really good. And so that's kind of what our practice problems kind of look like for that. I know that we're kind of running a little bit behind, so I want to jump ahead so we can kind of see some of these other questions. One of the things that I would definitely recommend is there's a part about solutions. Now, the hard part with solutions is a lot of what it focuses on for your ACS is going to be things like how you guys prepare it, your titrations, limiting reactions. What it doesn't have is it doesn't cover much on your colligative properties. But this will be on your final. So as we're going through with this part, I do want you guys to know how to do them, right? It is an important part, but it is something that's more on your final and less on your ACS, right? When you think about your colligative properties. So for most of your solution part, what you're more worried about is kind of like your dilution type of problems, how you do those concentrations, changing around your concentration units a little bit, things like that. So if we have time at the end, then I'll do some of those practice problems for freezing point and boiling point. So we're talk about, I'm trying to see if I have one. I will find a sample problem for that. And so we'll do that at the end if there's time. But I know that someone had brought that up in chat at the very beginning. I just wanted to to let you know that I had seen it. Is just not something that's as covered on the ACS. The next part, what we're going to look at is formula calculations in the mole. So empirical and molecular formulas, the difference between them, right? So empirical formula is always your lowest ratio. And this one is going to be the actual ratio of a molecule. Sometimes those are the same, sometimes they're different, because you might have more than one set of those ratios together. So like CH2 might be your empirical formula, but the molecule is actually made of 2 carbons and 4 hydrogens. So this would become your molecular formula. Right? So your empirical doesn't always match your molecular, but they can. And so some of these questions should feel like second nature to us by now. Like finding the molar mass of something, I hope that that's something that we can just do now. Okay. So these are some practice ones that we can try. So 1 mole of a hydrocarbon, which means that it's made up of just H's and C's, but we don't know how many of each, requires 8 moles of O2 to complete combustion to give carbon dioxide and water. Think about what it means when it says combustion, and it also gives you the products there. So we should be able to balance that equation. We have about 15 seconds left. All right, that's going to be our time. You guys seem evenly split through all of the answers, right? So let's look at a combustion. So a combustion means that we're going to have oxygen gas, and we're going to have this compound CXHY, and we're making carbon dioxide and water. Now, the thing that we know about this is that we should have 8 of these oxygens in order for all of that to balance out. Now, if that's going to balance, we need to think about what values we can put in those other ones. Now, if I put carbon as being 4 here, that uses up 8 of my oxygens. How many oxygens does that leave left over for my water? What do you guys think? If I put a 4 here for my carbon dioxide, that uses up 8 of my oxygens. How many oxygens do I have left over for my water?
Would it be 4?
We would have 8 left over because we have a total of 16 oxygen. Right? Now, this is just giving me an idea of how I can start to find what those other values are. Right? So if this gives me 8, then I would have a C4H8, something like that. Now, that's obviously not one of my options down there. And so I might try to go on to my next one. So there's 2 things that this tells me. Is one, that this can't be B because we wouldn't have enough H's. Or sorry, it wouldn't be 8 hydrogens, it would be 16 of them. It also tells me it can't be A because we, if we were only C3, we wouldn't have C3H8. We would have way too many H's left over for that as well. So I can move this up. I can change this to 5. If that becomes 5, then what does my H2O have to become? What do you guys think? If I put a 5 in front of my CO2, how many oxygens do I have left for my H2O?
Five.
So 5 for the CO2 is 5 times 2 for the oxygen, so that's 10. And so it's not that we have only 5 left for the oxygens, we should have 6, right? Because we have a total of 8 times 2 for the oxygen, so we have 16 oxygens total. Right? So that means that this becomes C5 and H what?
C5H12.
Very good, C5H12. And so that's how we got to D. Right? So for a question like this, where there's a little bit of guess and check that kind of goes into it, you notice that I didn't start with C3. I didn't start with my smallest one. Instead, I try to choose one that was kind of in the middle. Because if you get it right the first time, then great. But it lets me know I can like kind of eliminate 2 of the options with just 1 attempt, right? If you start at C3, all that does is it eliminates C3, but it doesn't tell me whether it's going to be C4 or C5, right? If I start with C4, then I know that that could be either C3 if it's too big or C5 if it's too small, right? So kind of one way to kind of look at that. Let's try our next one. So we're looking at question number 2 here. So we're about 45 seconds in. And this is going to be 90 seconds right there. So this is a good example of something that I might flag for my second pass, or I might do it. Just depends on how comfortable you feel, right? So if you were able to know right away your values and you could get through this in your 90 seconds, then I would recommend doing it on your first pass. If this was something that you knew how to do, but you're still calculating it right now, then this might be something I would circle and come back and do my second time around. Just so that way I don't spend too much time on each question. I can always come back and get this one a little bit later. Whereas some of those other conceptual ones, we've been able to go through a lot faster. And so you can make sure that you don't leave any of those behind, right? So it's about monitoring your time. So for this, if we have grams and we're trying to get to a concentration in moles per liter, what do we need to do to the 7.50 grams in order to get it to moles?
You're divided by its molar mass.
We got to go from grams to moles, so we got to divide by its molar mass. And so that's going to be about 111 grams. It's like 110.98. And then once we get that, we can just divide it by our volume, the 350 milliliters. Once we get into liters, so it's 0.350 liters. And that's how we can get a molarity. And so that's how we get to B. Any questions on that? Very good. So it seems like a lot of you guys know how to do it. It's just about making sure that you keep track of your time. Let's look at this next one. Question number 3. And that's going to be your 90 seconds. And so you can think about your time on this one, about how you kind of did with finishing it or not. And so this one's a little bit tricky. There's kind of a lot going on with this, right? Now, a lot of you guys are putting down aluminum, right? And aluminum, it's because we think that it has a +3 charge, and so that looks like it could be possible, right? We also have gallium, which could be a +3 as well, right? Chromium can make a +3 compound, and so can scandium, right? So just be aware that if you're just guessing based on their charges, it's not a bad way to go, but there is a mathematical way for us to solve it as well. So if our compound for our zinc is 0.422 grams out of 0.797, this is going to tell me what percentage of it is just my zinc or my element Z. So 52.9%. Right? That means that the other part, 47.1%, is my oxygen, or just O. So if I want, I can take that oxygen, 47.1, I can multiply it by the atomic mass of our oxygen. And so what I'm going to do is I'm really going to multiply 47.1 times O3. What this is going to do is it's going to take my, if I had 47.1 grams of my oxygen, it tells me how much O3 in moles I would need. And then once I have that, my numbers of moles, I can multiply that by 2. And I can take 52.9, divide it by that answer, and it tells me what my molar mass should be. So 52.9 divided by 2, and I get something like 26.9, which ends up being our aluminum. So what I did was I figured out how much oxygen I had. I've used that to figure out how many moles of O3 that would be. And then I can use that to figure out, well, what the molar mass of my Z should be to balance that out as well. Any questions on that part? That's one way to do that. There's other different ways to kind of make that same problem. Right. This is going to be our next one. So one thing, it's saying what mass of one atom, and then it wants us in grams per mole. And so that should trigger something in your mind, right? So what do we do if we want to convert our grams per or our grams per atom into grams per mole?
Avogadro's number.
Avogadro's number, and Avogadro's number is 6.022 times 10 to the 23rd. And that's going to be our 90 seconds there. So what we should do is we should take that 1.71 times 10 to the negative 22, and we should multiply it by Avogadro's number, because this is atoms per 1 mole. And so if we want to get moles to the bottom, then we just need to multiply it by that. And so when we multiply it by that, then we should be getting 103. It comes out to like 102.97 grams per mole. So all I did was I took that and I multiplied it by 6.022 times 10 to the 23. So just remember, anytime they talk about molecules or atoms, you want to be thinking, maybe we need Avogadro's number, right? That's how you go from the individuals to the mole. Let's look at this next one. What percent by mass of nitrogen in ammonium carbonate, or what is the percent by mass of nitrogen in the ammonium carbonate? So we're about a minute in. And that's going to be our 90 seconds, right? Now, for something like this, there's two things that we need to find. We need to find the total mass. So that's going to be the molar mass. And then we have to find just the mass of our nitrogen. Now, if time is becoming an issue for you, there's something that you can do for this type of test, though it doesn't always work for all of our types of tests. And it's about how we know when we find a molar mass, how much precision we need with it, right? Now, because this is multiple choice and these number differences are pretty big, when you're going through, you might just use the first, like the whole numbers of it, right? So what that means is that for when I find this molecule, I might take 14 for my nitrogen, 4 for my hydrogen, multiply that by 2. So that's 36 plus 12 for my carbon plus 15 times 3 for my oxygen. And I get a mass of 93 grams. I know 14 times 2 is my amount for my nitrogen, so that's 28. And so 28 divided by 93. This gives me 30.1, which is right along there. And so sometimes that's a way to just get through those numbers a little bit faster, is to not go quite as in depth as you normally would. It's not necessarily what I would always recommend. Oh, sorry, this was a calculation. This should be 96. And then we get 29.2. But it's one way to kind of speed up those calculations. So if you're really struggling with your time, you can also think about maybe we don't need to put in all of those numbers. It's not generally what I like to recommend because I always like to have as much precision as I possibly can, but I do recognize that time is a challenge with this type of exam. Do you guys have any questions on that? There's some more additional problems like that inside the slide pack, so you can keep going with them. But we're going to move on because there's a couple more topics I want to make sure that we touch and we talk about before you guys are on your own. And so stoichiometry is another big one. Stoichiometry, there's a lot of math associated with it, but it is like the backbone of what we do. So it is something that you want to make sure that you know how to do, because I would say that it's probably one of the big 3 pillars of what we need to be able to accomplish from Chem 120. So I can guarantee you that there's going to be questions about this both on your ACS as well as on your final exam. And so let's try number 8. So about a minute in. All right. So when you're looking for something like this, this one is where you want to make sure that you've kind of like collected some of that extra time. And so sometimes that's why it's important to make quick decisions about whether or not you can tackle a question or not, right? For this, we have to kind of do 2 things. We need to write out our equation, we need to balance it, and then we're going to do this next part of converting into moles. So combustion is always going to be something similar where we're taking that oxygen as our reactant, and then we're making this into CO2 and H2O. The nice part about this is your number of carbons is your number of carbon dioxide. Half of your hydrogens is your H2O. And so now when we balance that, we should have 6 oxygens, 10 oxygens total. So we need a 5 in front of that. So now I just need to take my 2.2 grams and turn that into moles. So that becomes 3 times 12 plus 8 times 1. So this is 44 grams per mole. So 2.2 divided by 44. And then I need to do that conversion where I need 5 O2 for every 1 C3H8. And so we need 0.25 moles. And so that's a way to kind of get through all of those. Now, it is a longer problem, right? There just is a timing thing that's related with that one. So this is definitely one that I would come back and do on my second pass, especially if I didn't feel comfortable with coming up with my equation right away, right? There will be other questions in there that you would be able to do instead. And so I would be coming and trying to get these on my second pass because I know how to do this, but it does take a little bit longer. I need to put more thought and more calculations. And so what I don't want to have happen is I don't want to get stuck on this problem for 5 to 10 minutes, get this one, but then not even look at my last 10 problems of my exam. So in some ways, it's like a numbers game. Let's go ahead and look at number 9. And so number 9 is saying that we have a polyethylene bag, right? So a plastic bag, and it weighs 12.4 grams. And they want to know how many molecules of C2H4 have to be put together. That's what polymerized means to make this bag. Right? So it's using just an unusual word in that case. So it's saying how many molecules of C2H4 have to go together to make that bag. You can think of it in some ways that you're starting from grams and you're trying to get to molecules. And so how would you typically do something like that? If we start with grams and we want to work our way to molecules. So we're coming up right on 90 seconds. So if we have grams and we want to get to molecules, it means that we're going to need to go through moles. Now, we know that if this is 12.4 grams, if we had 1 mole of C2H4, that would be 28 grams. And we know that every 1 mole is 6.022 times 10 to the 23 molecules. So if we take that 12.4 and we divide it by our 28 and we multiply it by our 6.022 times 10 to the 23rd, we can find out how many of those molecules we need. So we need 2.67. So if this problem really threw you off because you weren't quite sure, is look at what they give you for your givens, right? So they gave us grams, so that's how I got up with this side on the left. And then we needed molecules. And sometimes just looking at the units can kind of help you get an idea about where things are going. In the same way that they start with grams of one thing, and then we ended up in moles of another, I knew that I needed to get my grams into moles. That was going to be half my battle. And then I knew I needed something to get my moles of C3H8 to moles of O2. Right? So you can keep those in mind as you're working between them. You can also have stoichiometry problems that kind of look like this. So this is a stoichiometry problem combined with an ideal gas law. You have about 15 seconds left. I'm going to let this one go a little bit longer, but think about if you do a stoichiometry problem, you're going to need to get it from grams into its moles before you can solve it. So I'm going to start solving it through on this. Right? And so let's look at what we have. We know that we have 25.5 grams of NH3 and we have 36.5 grams of HCl. So one thing that we can do is we might as well just turn those into moles. So this is going to be 17 grams per mole for my NH3, and this is going to be 36.5 grams per mole for my HCl. So 25.5 grams divided by 17 becomes 1.5 moles. 36.5 divided by 36.5 becomes 1 mole of HCl. So do we use up both of these reactions completely, or reactants completely, or do we have some left over? What do you guys think? Do we use up all of our reactants, or do we have some left over?
Some left over.
And what do we have left over? Is it going to be HCl or is it going to be NH3?
NH3.
NH3. And we can see that because of this equation here, right? So it's a balanced equation. And so we need 1 mole of NH3 for every 1 mole of HCl. So when it goes through this reaction, because it's saying it reacts completely, then we have 0.5 moles of NH3 left over, and we used up all of that HCl. Now, what state is our NH3 in? Is it a solid, a liquid, or a gas?
It's a gas. Right?
It's a gas. And so the gas is the only one that we need to worry about when we're looking for pressure. So if we want pressure, we want to be thinking gas. So if we have 0.5 moles of gas at 85 degrees and the 5 liters, we should be able to figure out its pressure. Pressure is PV equals nRT. So we should be 0.5, our R value 0.08206. Do we need to do anything to our temperature? Or can we leave it as 85? What do you guys think?
Convert it to Kelvin.
We have to convert it to Kelvin. So this becomes 358.15 Kelvin. And then after all of that, we can divide by our 5 liters. So 0.5 times 0.08206 times 358.15 divided by 5, and we get our ATMs, 2.94. So this is a hard question to do in 90 seconds, right? Even when I do it, it takes longer than 90 seconds. Right? So when you look at your ACS exam, it's kind of split into 3 categories of questions. There's easy, medium, and hard. Right? Even if you know how to do the hard ones, sometimes it's hard to do them in the time constraint that you have. And this is why I really encourage the 3-pass approach, is because there will be ones that you can do, but they might just not, they might take you too long to do right away. And so if you have extra time, then you want to go back and tackle these. If you don't have that time, you want to make sure that you take care of all of these easy ones first, all of those medium ones, and then tackle the hard ones at the end, right? And so just keep that in mind as you kind of go through your questions. And that has to deal with the style of test that this one is. So we're going to look at our solutions. We've talked a little bit about them, right? But now let's look at an example of one. And so we want to make a 0.4 molarity solution of NaCl. So we have about 15 seconds left. So when we think about dilutions, right? Dilutions, if we add in other volumes, we're only going to get more dilute, right? So like, let's take C for an example. C can't be our answer because we're starting off with 0.4 and then we add more water to it. So we're going to end up even more dilute because our moles stay the same, but our volume has increased. Now, some of you guys are saying A as your answer. Now, A, we do get 0.4 moles of our NaCl, right? In some ways, if you would look at that. But each of those solutions, when we add them together, they don't stay at 500 milliliters, right? They're going to increase. And so we are going to double the volume, but our moles stays the same. So instead of being 0.4, this is really going to make a 0.2 molarity of that NaCl. Because we had 0.4 moles per liter when there was 0.5 liters, and now we're up to 1 liter. So it's not going to be A. For these other ones, we have 300 milliliters of NaOH, so that's going to be 300 times 1.2, and 600 times 0.6. So both of them give me 0.36, and then we have 0.9 from our liters. And you can see how we get to 0.4. Okay. The last one is we start off at 0.6 molarity, and we went from 400 milliliters to 1,000. So 0.6 times 4 divided by 10, or 400 divided by 1,000. This gives us 0.24 molarity. So when in doubt, when you're trying to find these calculations, is turn them into moles. So take their values, multiply them by their volume, and then divide that new volume by your, or divide that number of moles by your new volume, and you can get there into their concentration. Right? So we should be looking for B in this one, for that part. Now, one thing to say is if everything's in milliliters, you can leave everything in milliliters. If you have milliliters and you want liters, or if you have liters and you want milliliters, then you have to take that into account. But in the same way, if I take 300 times 1.2 and divide all of that by 900, it will cancel out when we get to our molarities. So that's okay as well. Let's look at that next one. Which solute will give us the highest boiling point? And so this is our first one with some colligative properties. Now, there's not really that many on this exam, so it's not something you have to know for ACS. But it is something that can help you for your final. It's about a minute in. So when we're looking at this one, when we think about boiling point, is boiling point going to increase when we add in more stuff into solution or decrease? What do you guys think for our boiling points? Is it boiling point elevation or boiling point depression?
Elevation.
Boiling point elevation, very good. So the more stuff we dissolve, then the higher the boiling point is going to become. And you can kind of know that we're talking about this is because we're talking about the solution, right? If it was just talking about individual materials, so if it was like water compared with isopropanol, compared with ethanol, then we have to think about their intermolecular forces. But if we talk about solutions, then really you're just thinking about how this stuff dissolves. Now, all of these, are they electrolytes or non-electrolytes?
Non-electrolytes.
Non-electrolytes, which means that they all are going to do the same thing once they're dissolved. They're all going to have this Van Hoff factor of 1. So if we want the highest boiling point, we want to have the most moles dissolved in there. So if they all have the same amount of mass, which one is going to be the highest number of moles? Is it going to be our highest molar mass or our lowest molar mass? So if I have 50 grams of something, and if one of them has a molar mass of 5 and the other one has a molar mass of 50, which one is going to give me the more number of moles? The bigger number or the smaller number?
The lowest.
The lower one. So from these four options, who's got the lowest molar mass?
D.
D. And so that's how we're able to come up with our answer as D, is we want the lowest molar mass in this case, because that's going to give us our largest number of moles for the same mass. And that's going to give us our highest boiling point elevation. Right? And so that's the thing to keep in mind when you're going through those, is that's what you're trying to measure them against. Now I know that we've kind of run past our time. I'm willing to stay and where you can go through. We still have enthalpy left, and we also have structure and bonding to kind of talk about. So if you can't stay, that's fine. I'm going to post the recording of this onto YouTube as well, so you guys can go over that as well. If you have time to stay, then you can always stick around and we will work through some more of these type of questions. There's also, I think we've done maybe half of the questions that are on here. So if you just want more practice ones, then you can also work through these slides on your own, and then you have the answers with them as well. All right, then then we're gonna go on to our heat and enthalpy section. And so this is all of that calorimetry type of stuff. This is about Hess's law, things like that, the delta H of a reaction. So let's start with this first one. Let's look for this delta H of formation of SiF4 as a gas.
Hey, aquí olvídate.
You have about 15 seconds left. All right, so we'll walk through this one together. Right? Now, when we're looking at this, when we're looking for delta H, we know that this entire reaction has this change here. Now, whenever we're thinking about enthalpies, and whether that's with our heat formations or with our bond averages, right, we should be thinking about something. Right? And that equation is going to always be that it's going to be our products minus our reactants. So if we add up all of the delta H's for our products and we subtract from it all of the delta H's for our reactants, it should be equal to that for our reaction. So for this question, we know that our delta H for a reaction is 4.6 kilojoules per mole. And that should be equal to SiF4, which is what we're looking for, plus 2 times waters minus SiO2, so that's negative 910.9, minus 4 times and then negative 320.1. Now, if you wanted to, what you could think about is you could think that this is really an addition sign here, and then you would have a bracket there. But sometimes what I notice is that people are more likely to make a small mistake where if you don't put those brackets in, you end up adding in the HF instead of subtracting it. So I just go ahead and leave it as a minus. So I subtract each of my reactants separately. And so now we're going to try to rearrange these to kind of solve for this delta HF of our SiF4. So I'm going to consolidate. So I take that 4 times negative 320.1, or sorry, 2 times negative 285.8. I subtract from that that negative 910.9. I subtract from that 4 times negative 320.1. And so I'm getting something that looks like 4.6 kilojoules per mole is equal to whatever this delta H of formation is for my SiF4 plus 1619.7. When I take 4.6 and I subtract my answer from that, then I get negative 1615.1 is equal to my delta HF, which can be my answer. Do you guys have any questions on that? Because it looks like no one was able to get a response for that one. I'll leave up the slide with the work if you want to see it. Did you guys have a part of that that you would like me to go over again? Or do we feel pretty comfortable and now you guys just want to try another problem on your own? Okay, then let's try some calorimetry. All right, and that's going to be our 90 seconds. So what equation comes to you guys' mind when we talk about calorimetry?
I was thinking MCAT.
MCAT, right? So we have the heat of something is equal to MC delta T. And delta T, how can we write that in terms of initial and final temperature?
Parentheses TF minus TI.
TF minus TI. So it's always final minus initial. Now, what's going on here is that we have a sample that's a mixture of iron and titanium. So it kind of makes this part a little bit more tricky in some ways, and in other ways we can kind of simplify them, right? So what we could do is we know that there's 200 joules, so that's our Q. And we could separate it into two kind of equations. We know that they're going to have the same initial and the same final temperature. And so that delta T could be the same. But what changes is their mass and their C. So we could say that the mass of iron, 10.0 grams, times its heat capacity, 0.461 joules per gram Kelvin, means that for every change in our delta T, this is how much energy our iron would need. 4.61 joules per every Kelvin or degree Celsius. And our titanium is going to be 10 grams as well, 0.544 joules per gram Kelvin. And so that one becomes 5.44. So our whole block is 4.61 plus 5.44. And so our block takes 10.05 joules per every change in Kelvin. And then I'm going to go ahead and erase this so we have some space. All of that is equal to our change in our temperature, which is our Q. So our Q is going to be the 200 joules. So we have 200 joules to spend. We are losing, or it requires 10.05 joules per Kelvin for each change in our temperature. Now we can update our TI as being 100. So if I take 200 divided by 10.05, that means that we're getting a change of 19.9 Kelvin. And so my TF must be, oh, sorry, this should be negative. Must be 80.09 degrees Celsius for this change, which is going to be our 80.1. So all I did was I consolidated our specific heats based on their mass. So basically I took that Q equals MC delta T. I simplified that part down first, and then I plugged that in to find my change in my temperature because they're both going from the same final to the same initial. You could have also done it as a series of two equations. So Q is M iron, C iron, delta T iron, plus M titanium, C titanium, delta T titanium. And then you'll find out that the delta T's have to be the same because we are starting at the same initial temperature and at the same final. But I find my way to just be a little bit easier. It's less math that I have to like kind of consolidate down. Some of them will also just be a little bit more conceptual. So you might have a question that looks like this. So which of them is going to have the greatest entropy at a given temperature? So they're all at the same condition. Which one is going to be our greatest entropy? And so remember that entropy is disorder or randomness. So when we think about this, between a solid, a liquid, and a gas, who has greater entropy? between a solid, a liquid, or a gas. If everything else is the same, who's got greater entropy? So entropy is going to increase as we get more movement. So a solid doesn't have as much movement in it as a liquid or a gas. So solids have the lowest entropy. Liquids is the second, and gases are the most. So if we want high entropy, we're going to be moving towards gases first. And then we want to think, well, which one has greater entropy? When we separate the hydrogens away from the bromines, or we allow them to be mixed as HBr. The second part is also that this bromine is a liquid. So we would rather have 2 moles of gas than 1 mole of gas, 1 mole of liquid. And so that's how we came up with C as our answer, is that we want as much gas as possible. So you can have a mix of conceptual problems as well as calculation problems for this one, as you guys are going through them. Now, structure and bonding is kind of our next one here. So this is lattice energies, electronegativities. This is where you do Vesper, intermolecular forces, bond orders. All of that gets kind of tied into in this section here. So all of those sections that we've kind of gone through, this is our, we have states of matter as being our last section after that. All of these are going to be on your exam or on your ACS. There's also a summary of these big topics in the review for today. If you go down to the bottom, it tells you the main ideas for the ACS, and that's where you can find this one as well. So let's go through and let's decide we know that there's a big increase in their, there's an increase in their boiling points between each of these molecules. And so we would like to know why. Why is there an increase between them? So when we're looking at these, what we want to think about is what part is changing. So for these molecules, do they seem like they're made up the same way? Or do they look like they have completely different type of groupings in there, right? That means like, are they all going to be polar or non-polar? Or does it look like we're going to have a mixture of polar and non-polar for them? What do you guys think? If we look at what we have, right, they all kind of start off in the same way. The only thing that changes is that last part. We add more carbons and more hydrogens to them. So is that going to change things like our polarity, or is it kind of just going to make the molecule bigger and bigger? What do you guys think? So as we add in those carbons and those hydrogens, we're not really changing things like the polarity. We're not changing them as new molecules in the way that if we had something like PF3 versus NH3 versus PCl4, right? Those are changing connections. And so then we might be looking at, well, some of them are polar, some of them are non-polar. Or we might have a hydrogen bond where the other ones don't, right? This one isn't like that because they don't have a big change. We're not adding in hydrogen bonds. They all either have it or they don't. We're not adding in polarity. They all either have it or they don't. What we are doing is we're making one larger than the other. And so which of these forces corresponds with your size of your molecule? So that could be because it's got more electrons or if it's got a larger molar mass. Which of those forces corresponds with that?
London forces.
London forces. And so that is B. The other ones aren't tied in with our size of our molecule. And so that's not going to be what's driving that process. They also have ones that talk about our geometries. So let's look at this one. And so we have to look at the geometry of the carbonate ion. So what do you think that you guys need to do for this carbonate ion in order to answer these questions about it? So if you want to answer things like bond distances or bond angles, the thing that you have to know is you need to know its Lewis structure. So if you don't know the Lewis structure, it's going to make it hard to do anything else beyond that. Once you guys have your Lewis structure, then we can fill in those other parts about it. And so you want to ask yourself, well, do we have any resonance, or is our Lewis structure the only one that it can have? So carbonate Lewis structure looks like this. Now, does it have any resonance structures?
Yes.
It does, right? So we could have it either with the double bond facing up. We could also have it with the double bond facing to the right. We could also have it with the double bond facing to the left. So it's got resonance for all of those, right? Now, when we look at this structure, what basic electron geometry does our carbon have? What would be the basis of that electron geometry for the carbon?
Trigonal planar.
Trigonal planar. So if it's trigonal planar, what are the bond angles between it?
120 or
120. So that's good. So that's how we get the bond angle part. So we know that they all have bond angles of 120 because they're evenly spread out. Right? So we know 2 is going to be true. And then let's talk about bond distances. So generally, double bonds would be shorter than single bonds. But because we have resonance, so that double bond could be between any of them, it means that all of their bond distances should be the same because they should be evenly spaced out between all of that carbonate. And so we are looking for C for our answer because it has the same bond distance as well as the same bond angles for all of them. Let's look at our next one. Which of these has the trigonal pyramidal geometry? So what I would do is translate this into how many electron groups, and then split up your electron groups into how many atoms attached versus how many lone pairs. So trigonal pyramidal, that means we should have 4 electron groups, 1 lone pair, and 3 atoms. So PCl3 looks something like this. The bond there. BCl is not going to have a lone pair on it. IF3 is going to have 1, 2, 3, 4, 5. So it's got 2 lone pairs on it. And then SO3 has double bonds between all of them. So it's got 3 atoms and no lone pairs. So when we really look at this, the only one that's 3 atoms and 1 lone pair is going to be our PCl3. And so that's going to be the only one that we have. That's going to be our trigonal pyramidal geometry. Now, one way that I can kind of get through those so quickly is I think about my number of valence electrons. If I'm looking for 1 lone pair and 3 atoms, that's generally each of those atoms is 1 valence electron, and the lone pair is 2. So that's how I get to 5 valence electrons. It's not always the case, but it's at least giving me a starting one to start with. You can see that IF3 is 7 valence electrons, right, for iodine. And so that's how it gets 3 atoms. And then we would have 4 left over, so that's 2 lone pairs. So you can kind of see how those things are kind of connected. The last topic that we're going to kind of get into is our states of matter. And so it's states of matter, the big part about it is it does cover our ideal gas theory, but it also does a little bit about phase diagrams. Right? So you do want to understand those 2 parts. So we're going to do these last 2, and those will be our last 2 problems that we kind of work through for today. Though there are a lot more practice problems in there as well. So we have a vessel. It contains 66 grams of CO2 and 16 grams of O2 at a pressure of 10 atmospheres. What is the partial pressure of CO2? Now think about this part. If we're thinking about partial pressure, we want to be thinking moles. So what mole fraction is our CO2 compared to our O2? So because I want moles, then I'm going to convert my 66 grams to moles. So I divided it by 44, and that becomes 1.5 my 16 grams. I converted that, and this becomes 32, or sorry, 0.5. It's 16 divided by 32. So now I have a total number of moles of 2. I have 1.5 for my CO2. And that's letting me know that out of my total pressure, 75% of it is going to be from my CO2. So if I take 10 atmospheres times by my mole fraction, 0.75, I can find the partial pressure of my CO2, which is C. Do you guys have any questions on that part?
Could you explain how you got 1.5 and 0.5 again? My bad.
Sure. I took the grams of the CO2 and I just divided it by its molar mass. So
Okay.
CO2's molar mass is 44 grams per mole. So I took 66 and I divided by 44.
Okay, thank you.
And then for the oxygen, just make sure that you do the 2 oxygens,
Mhm.
because if you ended up with B as your answer, you made the mistake of just dividing it by 16, which
Not
threw off
30.
that part, right? So it should be 32 grams for the oxygen. So that's how you get the 0.5.
All right, thank you.
You're welcome. And then let's try our last question, question number 4. So we're looking at an airbag here. So automobile airbags, they used to be made by this decomposition. So we want to know what mass of this we would need to put in to make a bag that fills up this. And if you look, this is a question that you've had on a quiz before for us, maybe not with these exact numbers, but it's a question that we've definitely covered. All right, so that's going to be our 90 seconds. So when we're talking about the airbag, what material or what chemical is going to be making that airbag, like the pressure in it? Is it coming from the sodium azide or is it coming from something else?
Sodium azide.
So the sodium azide is not actually the thing that makes the pressure, right? That's our starting reactant. The thing that's making the pressure is going to be the nitrogen. So you just want to keep that in mind because that's going to be the key to getting to the second part, right? Is because we don't want to just turn this into moles. That's not going to be the moles of sodium azide. That's going to be the moles of our nitrogen gas. So we're going to take this, we're going to solve for the moles. N equals PV over RT. Now, when we do that, then our pressure becomes 1.2 times 16 divided by R. And then we need to divide that by our temperature, which we should have in Kelvin. And so this N becomes 0.8068. So that's our moles. Now we might make the mistake and turn that right into our grams, and that gives us answer B. But what we should do is we should take those moles of our nitrogen now, and we should use this equation here to turn into moles of our sodium. So we need to multiply this by 2/3, and then that answer will multiply by 65. So we multiply this by 2/3. So 0.8068 times 2 divided by 3 times 65.02. And so we're really looking for 34 grams for our answer. And so you just want to make sure that you practice a little bit with that one. There's a lot of different types of problems that they can ask you for ideal gas law. These are examples of when we're like kind of using them with our stoichiometry and our partial pressures. They also have some other ones where they might give you the states of them and then they change the conditions and you have to look into that. And so that's pretty much it for our ACS review.